Hello, class. So on this video, we're going to start on Chapter 2, Section 6. So again, for those following in the book, Chapter 2, Section 6. In this section, we're going to see a method for solving, again, some family of differential equations that we won't be able to solve with current techniques that we have. Before that, let me just remind you that in the previous video, we talked about some theorems about existence and uniqueness of solutions for initial value problems. I know that they're a little bit theoretical, but again, I also talked about their importance, so hopefully you can see why they're important and go from there. I know it's hard, so hopefully the examples I did kind of show you how to work with a sort of theorem of this form. Okay. Now going back here to exact differential equations. Before we can go over that, I need to show you another thing that you're going to learn in Calculus 3. Okay. So we've already seen what a function of two variables is. We know that a function of two variables is just some expression involving the variables x and y in this case. We also know how to take the partial derivatives. We want to take the partial derivative of this function with respect to x, treat the variable x as the variable, right? So take the derivative as you usually would with respect to x, and treat everything else as a constant. Right? So the derivative of x squared would be 2x, the derivative of y plus 2, since we're assuming that y and 2 are both, that y is a constant, that derivative goes to 0. Similarly, partial f, partial y, take the derivative as you would normally with respect to y, treat every other variable as a constant. So in this case, for our purposes, x squared is a constant, so its derivative with respect to y is 0, derivative of y with respect to y is 1, and derivative of 2 with respect to y is, well, 2 is a constant, so that's 0. So we know how to do all these things. Oops. There's one more thing I want to show you that we're going to need in the case that the variables x and y are themselves functions of a single variable. Okay. So if f of x, y is differentiable, and again, kind of hard to explain here what differentiable means. I have to write it because it's an assumption we need. For what we're going to be using this definition, everything we're going to be working with is differentiable. Okay, so don't worry too much about the fact that it is differentiable. You just know that it is important, and that when you take Calc 3, you'll know what it means for a function of two variables to be differentiable. So if this function f of x, y is differentiable, and if x and y are both functions of a single variable, and that variable is the same for both of them, so x is a function of t and y is a function of t, then there is a way to interpret the derivative of f, the regular derivative, not the partial derivative that I defined in the previous section, but there's a way to interpret the regular derivative of f with respect to this single variable t. So again, there's a geometrical interpretation for this. There's a rate of change interpretation for this. For our purposes, I don't really care about what that means. What I want to give you is the formula, okay? So given this function f of xy is differentiable, again, for our purposes, all the functions we're going to be working with, for this are going to be differentiable. And given that x and y are both functions of a single variable t, then df, the regular derivative of f with respect to t, has this equation. Take the partial of f with respect to x, and then x is a function of t, so multiply that partial by the derivative of x with respect to t. Right? Add to it the partial derivative of f with respect to y. Again, we're assuming y is a function of t, so let's assume that we can take its derivative. Right? So that's something that I should actually add. So we should also assume that x and y are differentiable, because we can't take the derivative if they're not differentiable. Right? Assume that x and y are differentiable functions of t. Now this we can understand, right? We know how to tell or how to find differentiability for functions of one variable, so that's fine. Okay. Again, it doesn't matter much where this comes from. What I want you to focus on is on this equation. Let's do an example. So example 1. given that f of xy equals x plus 2y, and that x equals sine of t, and y equals cosine of t, find the regular derivative, so the derivative of f with respect to t. So by the previous definition, df dt is going to be partial of f with respect to x times the regular derivative of x with respect to t plus partial of f with respect to y times the regular derivative of y with respect to t. So just find each of those things and plug it into the equation. Partial of f with respect to x. Treat y as a constant, so this goes to 0. We can take the derivative with respect to x, and this goes to 1. So we have 1 times, now the derivative of x with respect to t. X is given by sine of t. What's the derivative of sine with respect to, sorry, there's a derivative of sine t with respect to t. Well, that's cosine t. So 1 times cosine t plus, now take the partial of f with respect to y. For this case, now you treat y as the variable and x as the constant, right? So the derivative of x with respect to y would be 0. The derivative of 2y with respect to y would be 2. So we have 2 times the derivative of y with respect to t. Y is given by cosine t. The derivative of cosine t with respect to t is negative sine t. Okay. So just simplifying everything, derivative of f with respect to t is given by cosine t minus 2 times sine of t. Again, you're going to learn more about where this comes from, how it works, how you interpret it in Calculus 3. For our purposes, what's important is that we know how to use this formula here. Okay. So this is basically the setup that we need for finding the solutions for a certain type of differential equation. So let's go ahead and try to do that. Actually, before I do that, I guess I'm going to stop here just to keep the video a little bit shorter. So I'm going to stop this video here. In the next video, we're going to try to find a solution, a general solution for a differential equation, and we're going to have to use this knowledge that we just learned about how this chain rule for a function of two variables works. Okay.